This is 9.3 part 2. So 9.3 continue. Again, this is the P series test. Again, you're going to have a series of the form 1 over n to the p power. Depending on the values to p bigger than 1 or less than 1, we can determine whether the series converge or diverge. Right? So we look at, there's a special case. Now, the special case one that we have considered is when the p power happen to be exactly 1. So you can have 1 over 1 to the 1 and 1 over 2 to the 1 and 1 over 3 to the 1. So it's really 1 plus a half plus a third plus a fourth. And because the p power is precisely 1, it still diverges, but we just have a special name for it we call harmonic series. So a harmonic series is a p series, but p is precisely 1. So in the expanded form, it will be 1 plus a half plus a third plus a fourth. And this series diverges very slowly. So it just means it's approach infinity really, really slow. Okay. Now, because the P series is so easy to evaluate later on, we're going to use it to compare with other series in the next sections. But let's take a look at at how we determine the conversion of series using P series. Look at this here. We have what 7 over into the 4th power, right? So again, that is the number 1. So to test the series, it looked like the P series, except the 7 is not on the numerator. Now, because it's the constant, right? So you can always take a constant out. Maybe you can rewrite that as 7 times. Again, it's just the sum. Right, so the same 7 times the sigma notation of 1 over the 4th, and from 1 to infinity. Now you can see this that's 1 over n to the 4th. That is a P series. Okay, it's power in the P series with, what is P? 4. So the P is big, 4 is bigger than 1. We can conclude that the series here converges. Notice that I can ignore 7 in front. It's just because this series converge, right? The sum of final number times 7 is still a final number. So technically, this one's the same, right? So with the 7 front here, but this converge, the whole thing converge. So that converges by P series. Okay. Now let's look at example 2. The example 2 here, you have 10 over q root of n. Again, you see the 10 is a constant that is unwanted, so you can rewrite, we take out the 10, and let's see what's left inside. That becomes 1, right? And that becomes n to the 1/3 power. Okay, 1/3 power. Now, we look at this. Once again, it is a P series with n equal 1/3. And 1/3 is smaller than 1. And since it's smaller than 1, the series converges. Oops, sorry, diverges. And backward. Diverges. Okay. Again, we reference this information here. P bigger than 1 versus P less than 1. Okay. Again, the P-series is pretty easy to use. Now, the notes on the integral test again. Sometimes the integral test, see the example that we did, it's pretty easy to check the three conditions, right? So we need these three conditions to be met or satisfied. Now, when you have a series with the formula that has an n on the top, then the problem is much harder to do. Why? So let's say you have this series n over Alright, so we have n over 2n plus 2. Or I can make it a bit more complicated, say it's n plus 5, 2n plus 2. Now, let's say it goes from 1 to infinity. Then you're like, okay, so the function that we consider is x plus 5 over 2x plus 2. Then check the continuous. Is it continuous? Not quite, because when x equals -1, we have 0 bottom. But again, since we start at 1, so we say for x bigger than or equal to 1, f of x is in this continuous. Okay, continuous. So that one check. Now, is it positive? Well, yes, because when x is bigger than 1, and these are positive terms, so they are positive. Now, these are easy to check, alright, so these two. The third condition is harder, is decreasing. Now, in the past, I don't do in detail why is it decreasing. It's just because there's no n on the numerators. But when that ends on the numerators, how do I know it's decreasing, right? So again, decreasing, to make sure you know or if function is decreasing when it's complicated, we have to use the derivative, the first derivative test. That is f prime of x. So recall, this is the coefficient, so u prime v minus v prime u over v squared. So derivative of the numerator is 1 plus 5, 0, minus integral of v is 2 times x plus 5. Right, so u times u prime v plus v prime u, don't forget everything's over the denominator is square. Okay, now why consider the derivative? Because I know that if the functions f of x, f prime of x, if that is positive, then we know that f of x is continuous. Sorry, if x is increasing. So it's going to be increasing. And on the other hand, if you check the first derivative, and if that's smaller than 0, then f of x is decreasing. And we need that statement. So we need to show that the derivative is actually smaller than 0 to conclude that this function is decreasing. Okay. Now, let's take a look. That's a 5. So do the first, I forgot the derivative. I'm gonna call it. Alright, so derivative of first is 1. Um, 5 times 2 is negative 10 there. So I have negative 10x minus that's 10, that's minus 50 over 2x plus 2 squared. Now I need to convey people that this quantity derivative has to be smaller than 0. Notice that the denominator cannot be smaller than 0 because it's square there. So that implies, in order for this to be true, negative 10 minus 50, sorry, negative 10 x minus 50 has to be less than 0. So negative 10 less than negative 10, let's take out so if that's less than 0, that means negative 10x minus 50 negative 10x so we have negative 10x here minus 50 less than 0, right? 0. 50 here, my ink right here. So here we have the numerator has less than 0, right? Because the denominator is bigger than 0 with the square. So you have negative 10x less than 50. So x is bigger than 50 of negative 10 is negative 5. So as long as x bigger than negative 5, then this derivative less than 0, so it satisfies all 3 conditions. Okay, so make sure you do that. Now, finally, I want to give a bit quick review here on some different tests that we learned earlier. Okay, so can you recognize the type of series to compare to use? We look at the first one, 11 over n to the cube of n. Again, with the 11, you can take it out. It's just 1 over. This is the n to the first, that's the n to the third. You add up, and that will be n to the 13. And you can see that this is a p series. With p is p 4/3, and 4/3 is more than 1. If the power series is more than 1, the series converges. You look at the next example. 2 over n over root 3 over n. Think about it carefully. We could rewrite these as n power. Right? So that's the same equivalent to 2 over root 3 to the n power. And when I see that, then notice that it is a geometric series. We multiply by the same number over and over again next term. And so this geometric series, the P will be 2. Sorry, I'm saying geometric series. Geometric series, we look at common ratio R. Okay, so that is common ratio is 2/3, but absolute of R is now more than 1. So the series diverges. Okay. Right. Then I'll do one more. Here's the next one. You see that 2n squared n squared plus 1. Now look at these, we call the divergency test. If you take the limit 2n squared over n squared plus 1, what do we have? If you take the limit of these and go to infinity, the top goes to infinity, bottom goes to infinity. Right? So one way to do is you can use a L'Hopital rule saying, well, we take the limit of this and this separately. So you have limits of taking derivative of 2n squared is 4n, and that is 2n. You can see that the n cancels over 2, now the answer is 2. I'm sorry, guys, I'm a bit sleepy. The answer is not 2. When the limit is 2, that means the term approaching 2, and by the divergent test, the series diverges by divergent test. Okay. Right, so that finished the part 2 of 9.1.